Good morning or good afternoon, good evening to everyone that's joining so far. To introduce myself, my name's Kevin Ward. I think I've met some of the people on the call, but hello to everyone. I'm a geologist by background, geology and petroleum geoscience. I'm the VP for Petrosys in the Europe, Russia and Africa region. And so it's my job to take you through depth conversion in Petrosys PRO today. And I'm just going to start with a sort of generic slide just to let you know about some of the resources that are available to our customers. The first is the website where we post newsletters and articles. So we'd encourage you to go onto the website, and you can sign up to receive these documents that will tell you kind of what we're up to here at Petrosys. The next area is the client portal, and if you're on the website, you'll find the link to get into there. I put a lot of workflows and various other parts to help you use the software on the client portal, and the workflow that I'm going to show today will end up on the portal at some point. And also LinkedIn, and I think that's probably how most people heard about this particular webinar, that and the emails. So do follow us on the LinkedIn. We tend to put a lot of our announcements on there. And finally, of course, you've got access to the support emails. Please contact support if you do need any help. So depth conversion in Petrosys PRO then, I'm not going to explain this workflow in too much detail in this slide because I'm going to show it all live. I've only just got this one slide just to introduce what I'm going to talk about, and then the majority of this webinar is going to be a live demo. So what I'm trying to show with the depth conversion in Petrosys PRO today, I'm trying to show that if you use the surface modelling workflow, such as the one that I've got here, this template workflow, that it really does four things for you. First of all, it's very flexible. Now it's flexible for different geological situations or different input data types or different software that's being used. The workflows are auditable in that we can save this workflow and we can prove what we've done to depth convert a surface maybe 6 months down the line or a year down the line when you need to look back and justify your decisions. You can save and reuse these workflows. The workflows are very powerful, so we can automate these workflows, and I'll show you an example of that today, where we'll look over some input data. And finally, the workflows are repeatable, and that's very important as well. It means we can take this workflow and we can reuse it in other situations or for other surfaces. And as I said, this workflow should end up on our portal at some point. And I've got my email address at the end. If you want to just ping me a quick email, I could email this across to you today. So the workflows are repeatable, used for different situations or for different surfaces. Okay, so that's it in terms of PowerPoint. I'm just going to go into the live demonstration. Let me just show you what I'm going to do today then. So I have some Petrel data. And in Petrel, I've got some seismic and I've got some fault sticks. And if I zoom a little bit further down here, you see I've also got some weld data. And I'm going to use this input data to generate this depth converted and tied surface. Now I can prove it's depth converted and tied because if I zoom in to some of these contours, you'll see this weld pick is at negative 1965, and you can see this is the negative 1960 contour, and it's negative 1980, and it's tied to the other weld points as well. So we're going to generate the depth converted surface, we'll generate the fault polygons, and we'll tie it to the weld data. And to do that, I'm going to make use of the surface modelling module, and this is really what the presentation focuses around. It's a 5-step workflow. It creates a two-way time grid from the interpreted data and also the fault polygons. It does the depth conversion, which is obviously the main part of this presentation. It performs a weld tie to calibrate to the weld data. And then step 4 and 5, I'm not going to cover today, although if you want to ask me questions at the end, I can go into that in more detail. But step 4 finds prospects by using the lowest closing contours tool. So it identifies the closures across the surface. And then finally, there's a volumetric step where we can do both deterministic and probabilistic volumetrics. As I said, step 4 and 5 I won't do today, but they are there if you want to discuss them at the end. So I'll start with step 1, which is about creating a two-way time grid from the interpreted seismic data. Now, as I mentioned throughout this workflow, I'm going to talk about it being flexible. So you don't necessarily need to create this two-way time grid. If you've already got it in Petrel or in a Kingdom or a different package, we can just use that and jump straight into step 2. But for the purposes of this demo, I'm going to start at step 1 and create the two-way time grid. So the first thing I'm going to do is just show you the first step, which is to create the surfaces one by one. And if I double click on that, I'll show you some of the key features of creating this gridding. So we create the input data from Petrel in this case, but if I click on this, you'll see that it doesn't necessarily need to be Petrel that we use as input data. We're very flexible for different sources. So if I add a new source in here, for example, my Seismic could come from various other sources, Kingdom, Dug Insight, OpenWorks, for example. Doesn't have to be Seismic. I can have two-way time data in my wells. I can have two-way time data as point data or spatial data, for example. So if I have data in an Excel file, I can use that. So it's very independent of the source and flexible to adapt to those situations. I then fill in things like input geometry. I can use different gridding methods in here. So we'll touch on a couple of these, kriging with external drift, for example. There's also bias gridding, so more advanced options, different algorithms. I'm just using the standard one here. But importantly, I am connecting to the fault sticks to generate the surface. So I've not created any fault polygons yet. If I had, I could use them. I'm just using the fault sticks though, and I'm connecting up to my Petrel fault sticks, and I'm going to save those as separate fault polygons and reuse those later on in the workflow. I'll skip the individual one by one example though, and I'm going to jump to this looping workflow. And the value of showing this is that it's repeatable and automated. So this workflow can be automated to generate all of your surfaces and depth convert all of your surfaces in a single run. If I double click, or if I single click here and run this part of the workflow, in fact, before I do that, let me open up this here. So this is my two-way time folder. So the grids will go into here. So you'll see this running as I do it. So if I click on this run icon here, I've set this up so that it asks me what my Petrel horizons are. And if I go inside here, I can select the Petrel horizons. So I'll just delete all just now, and I'll just add horizons. So I could select all of these horizons and loop over everything that's in my Petrel project. That might take 5-10 minutes to run, so I'm not going to do it in the webinar, but I'll just select two just so you can see it working. So top target, top edge. Click OK, click OK. I'll adjust the cell size, make it a little bit more sensible. And I can also use my fault sticks. You'll also notice in the software we have blue arrows, and if you're using Petrel or Decision Space, you can make use of these blue arrows. So if I just get rid of those fault sticks, if I go back to my Petrel project and select the fault sticks in there, then when I come back to my workflow, click on the blue arrow, it will populate only the fault sticks from that folder. So it finds those automatically, making the connection much easier to use. Now I'm going to click OK, bring up this folder again, click OK, and it's going to generate those two-way time surfaces for me now. And as I mentioned, I'm only generating two just to make it run a bit quicker for this webinar, but you could select 20 or 30 surfaces and it would generate you your two-way time grids for all of those surfaces in one run. So it's very powerful to automate this workflow. And just to touch on the fault sticks workflow, so as I mentioned, we're connecting to the fault sticks inside Petrel. So it's calculating the intersection of the two-way time horizon with that fault stick, and it's automatically generating the fault polygons for me. So I don't need to digitize those manually as you might do in other software. We can just use those fault polygons, fault sticks rather, and generate the fault polygons automatically, again speeding up the process of generating these surfaces. So right, so we've got the top target and we've got the top edge of surfaces created now in two-way time. Now if I drag this over here, I'm just going to display them. It's always useful before we actually start the depth conversion just to QC what we've done, make sure that nothing looks unreasonable. So I'll just drag those onto the map. And when those are created, I'll stick them into a group, just tidy up my display list a little bit. So this is my two-way time group, and you'll see that it's created both the grids but also the fault polygons. Now the fault polygons, we can export those straight into Petrel if we wanted just to get them back into Petrel. With the grids as well, the grids themselves and Petrosys PRO have the fault polygons already embedded in there. So I can make use of that in the display option. I can toggle on the contours I want. I'll just put on 20 and every 100. I'll just make it a little bit thicker with a label. And for the fault polygons, we'll just turn on fault symbols as well, so we can see those. And so I could now do various things in Petrosys PRO with the two-way tiled surface. I could present it in a map. I can also use the editors to edit particular contours or faults if they're not looking how I want them to. Or of course I could push it back to Petrel and work with them in there. Instead of doing that though, I'm going to jump back to the workflow and now get stuck into the actual depth conversion. And so this is what step 2 is. Now, as I mentioned, it's flexible for different situations. So I'm going to cover a lot of things in the depth conversion that I'm not necessarily going to run because I'm just using Seismic and fault sticks. But let's say, for example, I did have some velocity data. So what are my options in Pro? Well, there's two options. I might have weld velocities or I might have seismic velocities. And if I have weld velocity data, I can use the weld checkshot depth conversion option. And if I double click on that task, you'll see that we're connected to Petrel and it's automatically read the velocities and the time data from the checkshot surveys inside Petrel. And it gives me this nice table here, in this case for the top target formation. And within this option here, I can analyse that data in a chart. So if I just colour the points based on pseudo velocity, I can look at the correlation between time and depth. I can exclude any outliers. In this case, it actually looks not too bad, but let's say this was an outlier. I can exclude that selected point from the correlation. I'll just re-include it because, to say in this case, it's not too bad. And I can also choose different correlation types. So if you choose linear, you can also use things like polynomial, exponential, power, or logarithmic. And if I choose things like polynomial, I can choose the power of the polynomial. And what that does is it generates me a line of best fit, or a depth conversion equation, if you like, on here. We can also use the icons to push this image into a PDF or a PowerPoint if I want to use that as part of a presentation or some justification for my decisions. In this case, what I'll do is just accept this here, and I'll create a linked depth conversion task from this. So it takes the checkshot data from Petrel, takes the top as well that I've selected, creates that equation, and as a byproduct creates a grid arithmetic task. And in the grid arithmetic task, it automatically populates the coefficients of that depth conversion equation for me. So I can then go from my time surface that I've just created in step 1 to a depth converted surface in step 2. Now that's the example if I have weld velocities. If I've got seismic velocities, so stacking velocities, for example, then we also have a solution for that as well. And if I double click on this, I'll just show you this one here. It's creating a grid, and if I go into the input data and add some new data just to show you this as an example, I mentioned earlier the various things we can grid within Petrosys PRO. One of them you'll find down the very bottom of the list is stacking velocities. And when you're gridding stacking velocities, you can select segue files or ASCII text files, or if you have a corporate database software, you can also use that as well. So if I'm using a segue file, there's various formats that we support. And if I click on this, you'll see a list of them here. And if you would have a format, or you have a format that we don't support, you can always browse that file and define the format manually. And it's the same story for ASCII files as well. So if I click on ASCII files and just select an example, and click on select a format, you'll see that we support a range of formats like Western, TGS shell formats, SOV2, Discos. And of course, if we don't support that format, you can also create a custom format as well. So very flexible for working with different stacking velocity data in various different situations. I'm going to cancel out of that. I don't have any for this particular surface. And I'm going to go on to the next part of the depth conversion workflow, which is using derived equations. So we do see some clients using things like Microsoft Excel to generate or to derive their own equations. So they might be cross-plotting various data that comes out of like a sonic log, for example, and trying to find correlations between time and depth in those logs. If you derive your equations elsewhere, in Excel, for example, you can put those equations into the depth conversion equation in our grid arithmetic. And there's two advantages of that. First of all, if your Excel equations update, you can easily come in here and update them and rerun that task with different coefficients and different input data. Secondly, again, it's auditable. So if someone in 6 months' time asks you, how did you generate that depth conversion or that depth converted surface, you have proof of how you actually derived it using this task here. And it's also worth pointing out at this point that in addition to using your depth conversion equations derived from Excel, we also have a range of template depth conversion equations that you can use. So if I go to the depth conversion examples, we have things like V0 K, other situations like using salt layers. There's various equations in there that you can also use as well, and you can also customize these and share those template equations with other people. Again, I'm going to skip past that one though, and I'll go on to the examples where we have no velocity data available. Now, if you have no velocity data and no well picks, you can just use a constant velocity in the grid arithmetic. Probably not going to give you a very accurate surface, but if it's all you've got, then it is a possibility. If you do have well picks but no velocities, there are a couple techniques you can use. You can use Triggy with external drift. So that's one of the more advanced methods. And by using that, what you're doing is you're using the kriging functionality, but by combining with a two-way time grid as a trend grid. So you're kriging the differentials between the time and the depth picks on your wells. Not going to use that example here, although I could because I do have the data for it. But instead I'm going to use another technique called depth trend analysis. And if I double click on the first task here, and what I'm going to do is just toggle off this cross-validation report. I will talk about this in 2 minutes. And I'll just bring up the help menu to help me talk about that in a few moments. But this is very similar to the checkshot example that I showed earlier. The main difference is that it doesn't use any velocities, any velocity data. It's simply using the well picks and a two-way time surface. Now again, the two-way time surface can come from Petrosys. It can also come from Petrel or from any other source. In this case, I've already generated the two-way time surface in Petrosys. And it uses the well picks. Again, the well picks can be from a variety of sources. In this case, my picks are in Petrel. And what it does is it looks at the depth pick on the well, and using the XY coordinates, it calculates what the two-way time pick would be at that location based on your two-way time input data. And from that, it generates a pseudo velocity. And again, now that we've got the pseudo velocity, we could then analyze that data in a chart as we did before. And we can start to pull out outliers, or we can look at different lines of best fit to look at the correlation and generate depth conversion equations. Now, one other advantage of this method is that there is a good QC method available, and that is a cross-validation report. And if I toggle that on, it will generate the cross-validation report, and I can look at these numbers here and try to identify if there's any problems with these wells, any wells that don't quite fit that correlation. And if you use the help menu, this will give you a good idea of how to run through this. We teach this in our training, so it takes a little while to go through all of the theory behind it, but I'll try to explain it very quickly. Cross-validation is a technique where each well is removed in turn, and the outputs using all of the wells is compared with the result when you've removed an individual well. And what you're trying to look for is big differences between when all of the wells are present and when that individual well has been removed from that creation. So if we look at this as an example, this well B7 here, when we remove that and then generate the depth converted surface, there's actually about 250 meters of difference between that well being included and the well being removed. So this well is having a big effect on that depth conversion model. And if we look further across here at the R-squared estimate, so the correlation between time and depth, we'll see that most of the wells have quite a low, or most of the surface here has a low correlation. But if we remove this individual well, suddenly that correlation will jump from the 0.6 and 0.7s right up to 0.99. So this well by itself is actually having a big effect on the the correlation. And so what we'd want to do is either go back and check this well, or maybe identify that it's in maybe a different fault block, or there's maybe some salt involved and something's happening to the model around this well. So it's a good QC step. I'll just close this down and cancel out of this, and I'm going to run this depth trend analysis here. So to do that, let me just jump into the depth folder. There's nothing there at the moment, and I'll just run through this one here. So as it creates, again, it will give me this output. Again, I can save this and use it to justify my decisions later. I can choose different lines of best fit. I'm quite happy with the second order polynomial here. It seems to be doing a good job. That's fine. And then click OK, and it will run through this. And it'll also run through the depth conversion task here. So it will take that equation, it will apply it to my two-way time surface and generate this depth grid for me. So that's the depth conversion. We've now got a depth converted surface, and what we're going to do is tie this surface back to my weld data. We use the weld tie operation to do this. Now in the weld tie task, again, like everything else I've shown, we don't need to just use Petrosys welds. We can use Petrel welds. We can also use XL point data or GIS point data. Basically, any point data can be used to perform the weld tie. It also generates me a correction surface, and the correction surface is a good QC tool. So you can prove how much correction has actually gone into your depth surface to do the tie, because we can effectively correct the grid by thousands of meters, but there's no point in doing that, because then that means your depth surface was not accurate in the first place. So it's a good correction step, and it's a good surface to use to show how much correction has actually gone in to your weld tie. Now onto the methods option. There are 4 methods of weld tie in Petrosys PRO, and I'll go through these fairly quickly. But again, we offer training in this area if you wanted to learn more about them. There's the extrapolated method, which weld ties across the entire area of interest. And what it does is it performs a good weld tie at the weld locations, but it can often extrapolate to areas of low weld controls. You have to be a little bit careful about using it. There's the distance method, which performs at a distance around the point, so it won't tie by more than, in this case, 100 meters. There's the filtering option, which is like the distance method, but it uses a nearest point approach. So it only weld ties using the nearest point to the grid cells. And there's also the polygon method, where you manually digitize a polygon and tell the software to only weld tie within your defined polygon. In this case, I'm using the extrapolated method. I can click on scan here, and it will tell me that in this case, it's going to do a weld tie between -18 and +18 meters. So that seems reasonably accurate in this case. So my depth grid is sort of -2,000 meters, so it's only corrected by +18 meters. That seems fine. We can also apply some dynamic corrections if we want to apply minimum or maximum corrections to the surfaces. In this case, I'll just leave that at 0. That is fine. And the other very important thing in the weld tie method is the reporting. We generate mis-tie reports, and again, that mis-tie report can be included in a report to show how much correction actually went into your weld tie to justify your opinions. And if I click OK and run this task, we will see the mis-tie report pop up. And this is the mis-tie report here. So it shows you the Z value of the well. It shows you the value of the untied grid, the difference before, the newly tied grid, and the difference after. So we can see after performing this weld tie, we've got hardly any difference afterwards. So as much as maybe 16 centimeters of difference after my grid has been tied. And again, we can do some analysis on this. So we can analyze this in a chart. We can start to cross plot some of the values. Maybe look at the Z value on the wells versus the difference before, see if there's any correlation between depth and the difference. So we can do various things there to QC the weld tie. And as I mentioned, once you have generated this, it's important really to look at the correction grid as well. The correction grid, if I jump into my tied folder, so we've got the mis-tie report that I can use. We've got the tied surface, which I've shown already, but we also have the correction grid. And if I drag that onto the map here, and I might just need to adjust the contour slightly. to make this a little bit easier to see. So we'll display every contour. That should be okay. So we can look at this and we can see where the corrections have actually been applied. And you can see in this case, we have sort of 10 meters of correction here. I believe there's a well in this area. So you can see there's sort of 10 meters of correction around this well here. We can see that as we get up to this area here, the software actually extrapolates in this area here. So there is more correction in this area than we might otherwise want, and that's part of the extrapolated method. So where we don't have well control, that method might extrapolate, and so we might have to go back and try to control that process by applying minimum or maximum values. But that is really the essence of the creating the time, depth conversion, and weld tying the surfaces. As I mentioned, I can now go on to identifying prospects and doing volumetrics. Rather than doing that, I'll just go back to my slides. I just want to run through this final slide, make sure that I covered the key things I was trying to get across. So using Petrosys PRO surface modeling for depth conversion, first of all, it's flexible. So we showed that for different sources of data, whether it's betrayal or kingdom or segway or ASCII stacking velocities or different data availability, if I don't have velocities or if I don't have well picks, we have various flexible methods for depth conversion. It's auditable, so the surface modeling workflow can be saved and those steps and the decisions made can be justified at a later date. It's powerful. We can automate the process, saving you having to do steps one by one, and it's repeatable. So we can reuse this workflow for different surfaces or different projects. And as I mentioned, we'll get this onto our portal, but my details are at the bottom of the screen there. So if you do want a copy of it, send me a quick email and I'll just ping it across to you today at some point. I'll pause now and take any questions that anybody has. Perfect. Thomas, if you want to ask a question, feel free to unmute yourself and you can ask.
Could you just give us some guidance as to how to set up multi-layer depth conversions within Petrosys, please?
Of course, yeah. Let me share my screen again and talk through the screen. So I guess I focus on individual layers, but that's a very good point about multi-layer depth conversion. So under the grid processes arithmetic option, I talked earlier about using some of our template equations. If I clear this previous one and click on insert and go to depth conversion, you can use the average velocity equation. And if I click on that, that will just create a standard depth equals time times velocity corrected for the units. But if I also insert using interval velocity depth conversion, what that does is it creates a depth 2. Now, typically what I like to do is call this first one depth 1, and then the second one depth 2. And I can then copy and paste this second one as many times as I need for however many layers I want to use. So this third step would be depth 3, and then would be equals depth 2, and it would be plus the difference between 2 times 3 take away 2, and it would be the interval velocity of call it 3, 2. And if I use this blue arrow, what it's then saying is that it's looking for my first 2-way time surface, my second 2-way time surface, as well as the interval velocities between those, and it will, as an output, will generate depth 1, depth 2, and depth 3. So you sort of build it up as this kind of layer process, and then you fill in the blanks. And so you can have as many layers as you want, and it will generate a separate output for each of those layers. Not sure if I explained that perfectly. That we have some other documentation on the portal on this, but essentially this is the way you would do it. Does that help? Okay.
Okay, thank you. Yeah.
Okay then. Well, thanks everybody for joining. As I say, we'll get this video on the portal. If you do have any other questions or if you want a copy of this workflow, please just ping me an email and I'll get back to you. But thanks a lot for your time today, and hope everybody has a good day.